This is the story of the Karabiner 98k and why the truth is more complex than the legend. Late autumn, 1942. Somewhere along the approaches to Stalingrad, a German rifleman crouches in the remains of a collapsed building. Temperatures along the front have dropped well below -20 degrees Celsius. His fingers are stiff under wool gloves. Snow has worked its way into the folds of his equipment. He lifts his rifle, rotates the bolt handle upward, draws it back, pushes it forward, and locks it down. A fresh round feeds from the magazine into the chamber. In temperatures that could thicken lubricant and cause feeding problems in more complex mechanisms, this bolt still cycles. Not because of magic. Because of engineering decisions made decades earlier by a man who understood what failure looked like. That rifle was the Karabiner 98k, often shortened to Kar98k. And the bolt mechanism inside it was one of the most influential mechanical actions ever designed for a shoulder-fired weapon. An action so well regarded that more than a century after its patent filing, many of the world's premium sporting rifles still draw directly from its core design principles. Most people know the Kar98k as Germany's standard infantry rifle during World War II. They know it was bolt action. They know it held 5 rounds. They know it was accurate. But what most people do not know is why the bolt inside that rifle became the standard against which most 20th century bolt-action rifles were measured. And why, despite strong competing designs from Britain, America, and elsewhere, the Mauser action's fundamental architecture proved remarkably difficult to surpass for its intended purpose. If you are finding this interesting, hit subscribe. More deep dives like this are coming. To understand what made the Mauser 98 bolt distinctive, you first need to understand what a bolt-action rifle actually does. At its core, a bolt action is a manually operated repeating mechanism. The shooter lifts a handle, pulls a cylindrical bolt rearward to extract and eject a spent cartridge, then pushes the bolt forward to strip a fresh round from the magazine and lock it into the chamber. Simple in concept, difficult to execute reliably under combat conditions. The Mauser 98 action, based on a design patented by Paul Mauser on September 9, 1895, and formally adopted by the German military in 1898, addressed several problems that competing bolt designs handled less effectively. It did so through 3 specific engineering decisions that worked together as an integrated system. The first was the locking lug arrangement. The Mauser 98 bolt uses 3 locking lugs. 2 large main lugs sit at the front of the bolt head, positioned opposite each other. They engage matching recesses machined into the receiver ring. These front lugs provide the primary locking strength of the action, which means the bolt handles chamber pressures through front-mounted bearing surfaces close to the cartridge, which means receiver stretch and bolt compression are minimized compared to designs that lock at the rear of the bolt. Paul Mauser also included something that previous Mauser designs had not featured: a third lug, smaller than the other 2, positioned at the rear of the bolt body. This third lug serves primarily as a safety backup. Under normal firing conditions, it does not bear significant load, though manufacturing tolerances mean it may carry some minimal force depending on the individual rifle. Its main purpose is to catch the bolt in the event of a front lug failure, which means even during a catastrophic mechanical problem, the bolt is less likely to travel rearward into the shooter. The second critical feature was the controlled round feed system. This is arguably the characteristic that most clearly distinguished the Mauser from many of its competitors. A large, non-rotating claw extractor, machined from spring steel, engages the rim of the cartridge as it rises from the magazine. From that point forward, the extractor maintains contact with the cartridge rim. It controls the cartridge as the bolt pushes it into the chamber, holds it in position during firing, and maintains its grip during extraction, which means the Mauser action cycles more reliably when the rifle is tilted or held at unusual angles. A push-feed action, the type used in many other rifles, relies on the cartridge being pushed freely into the chamber, where a smaller extractor then snaps over the rim. Push-feed designs work well under most conditions, and modern push-feed rifles are excellent, but the controlled feed approach reduces certain types of feeding and double feed malfunctions, particularly when the action is cycled roughly or from awkward positions. This mattered to soldiers firing from trenches, from prone positions in debris, or while moving. It is worth being precise here. Controlled round feed is not immune to failure. If the bolt is not cycled fully and firmly rearward, the cartridge case may not eject cleanly, which can cause a jam. The system reduces certain failure modes. It does not eliminate all of them. Combined with a camming action on the rear receiver bridge, the Mauser 9.8 also provides strong primary extraction. When the shooter first lifts the bolt handle, a cam surface forces a slight rearward movement of the bolt body before full rotation. This mechanical advantage breaks the spent cartridge case free from the chamber walls before the bolt begins its main rearward stroke, which means swollen or sticky cases, a common problem with heat-expanded brass or moisture-affected ammunition, are pulled more reliably than in designs without this camming action. The bolt also cocks on opening, meaning the firing mechanism begins compressing the striker spring during the initial bolt lift. Paul Mauser deliberately reduced the firing pin travel distance compared to earlier designs, which improved lock time, the interval between trigger pull and primer strike. Both of these features, the camming extraction and the cock-on-open action, contribute to the smooth overall cycling feel that Mauser 9.8 users have described for over a century. The third notable feature was the gas handling system. Two oval-shaped ports are machined into the bottom of the bolt body. If a cartridge case ruptures or a primer fails, high-pressure propellant gases are directed downward through these ports and into the magazine area, routing them away from the shooter's face. A flanged gas shield on the bolt sleeve provides additional protection at the rear. Military versions included a secondary gas path along the locking lug raceway exiting through the receiver. And here is where it gets interesting. Paul Mauser had personal experience with what happens when a rifle action fails to manage escaping gas. In 1901, 3 years after the Gewehr 9.8 had already been adopted, Mauser lost his left eye when one of his experimental self-loading rifle prototypes, designated the C98, suffered an out-of-battery detonation during test firing. The explosion also broke his finger. It is important to note that the gas venting features of the Model 9.8 bolt action predated this accident. They were part of the original 1898 design, rooted in Mauser's long-standing concern with shooter safety across his earlier rifle iterations. But the injury reinforced that emphasis. His subsequent self-loading designs placed even greater priority on mechanical protection. The man who built what the National Rifle Association later described as perhaps the safest bolt-action rifle in the world was himself maimed by one of his other experimental weapons. There is a painful irony in that. Now, the Kar98k itself was not the original Gewehr 9.8. It was the final major military variant in a design lineage stretching back to 1898. The Kurz designation, meaning short, referred to its shortened barrel of approximately 23.6 inches compared to the original Gewehr 9.8's 29-inch barrel. The bolt handle was turned downward rather than projecting straight out horizontally, as on the earlier rifle, which means it required less clearance to cycle and was easier to operate quickly, which means the rifle could also accept telescopic sights mounted directly above the receiver, something impractical with the original straight bolt handle. Germany produced an estimated 14 million or more Kar98k rifles between 1935 and 1945, depending on the source consulted. The exact figure is debated, with some estimates reaching as high as 14.6 million. Production involved Mauser's factory at Oberndorf, along with numerous subcontractors including Gustloff Werke, Steyr-Daimler-Puch, Berlin-Lübecker, and others. But that was just the beginning of how this rifle's role played out on the battlefield. The common narrative about the Kar98k goes something like this. It was outdated, a bolt-action rifle in an era when the Americans fielded the semi-automatic M1 Garand. Germany lost the infantry firepower contest because they clung to a manual repeater while their enemies moved forward. The real story has more layers than that. German infantry doctrine during World War II did not center the squad's firepower on the individual rifleman. Instead, it centered on the machine gun, specifically the MG34 and later the MG42. The rifleman's role was to support and protect the machine gun team, engage targets at medium to long range, and provide accurate, deliberate fire. Within that doctrinal framework, a reliable bolt-action rifle was not an anachronism. It was a deliberate match for the assigned tactical role. That said, the rate of fire disadvantage was real and should not be minimized. Various sources cite the Kar98k's practical rate of aimed fire at roughly 10 to 15 rounds per minute in trained hands. The exact figure varies considerably depending on the individual shooter, the conditions, and whether reloading time from stripper clips is factored in. A semi-automatic like the M1 Garand could sustain a meaningfully higher practical rate. The difference was significant in many combat situations, and it would be dishonest to suggest otherwise. What the bolt action did provide was a natural cadence. Each manual cycling of the bolt creates a brief pause that some shooters use to reacquire their sight picture. Whether this inherently improved hit probability compared to semi-automatic fire is debated among firearms historians and marksmanship instructors. Some argue it encouraged more deliberate shooting. Others point out that well-trained soldiers with semi-automatics achieved excellent accuracy as well. The evidence does not support a simple conclusion either way. An estimated 132,000 or so Kar98k rifles were selected at the factory for above-average accuracy and fitted with telescopic sights for use as sniper weapons. The exact number is approximate and varies between sources. German snipers armed with scoped Kar98k rifles could be highly effective at disrupting enemy operations, particularly in defensive positions where patience and concealment mattered more than volume of fire. This is where the myth diverges from reality. The Kar98k's bolt-action mechanism was not the reason Germany lost the war. Germany's defeat was the product of strategic overextension, resource shortages, a two-front war against enemies with vastly greater combined industrial capacity, and numerous other factors that no infantry rifle, regardless of its action type, could have overcome. The decision to maintain the bolt action as the primary infantry arm was shaped partly by doctrine, partly by the enormous investment already committed to Kar98k production tooling, and partly by the logistical challenge of introducing new ammunition types for weapons like the Sturmgewehr 4.4. The implications were broader than Germany alone. The nations that fought against the Mauser bolt had already been influenced by its design. The American Springfield M1903, the standard United States service rifle before the M1 Garand, borrowed heavily from Mauser patents. The United States government ultimately paid Mauser approximately $200,000 in royalties, 75 cents per rifle and 50 cents per thousand stripper clips, under an agreement reached around 1904 to 1905. These payments continued until the agreed ceiling was reached in 1909. When the United States entered World War I in 1917, the patent situation became entangled with wartime seizure of German intellectual property. A post-war tribunal eventually awarded additional damages in a separate claim related to Spitzer bullet patents. The specifics are legally complex, but the underlying point is clear. American ordnance engineers studied captured Spanish Mauser rifles after the 1898 war and incorporated key Mauser design elements into their own service weapon. But this is crucial. Acknowledging the Mauser bolt's influence does not mean it was without peers or weaknesses. The British Lee Enfield used a fundamentally different approach. It locked at the rear of the bolt rather than the front, and it cocked on closing rather than opening. Its 10-round magazine held twice the capacity of the Mauser. The Lee Enfield's bolt travel was shorter, and its action could be cycled very rapidly. Well-trained British soldiers could achieve impressive rates of aimed fire. The rear-locking design created somewhat more receiver flex under pressure compared to front-locking actions, but the Lee Enfield was engineered to accommodate this within safe tolerances, and it served the British military reliably across 2 world wars. Both approaches had genuine merit. The Enfield prioritized speed and capacity. The Mauser prioritized locking strength and controlled feed. Neither was objectively superior in all conditions. They reflected different engineering philosophies shaped by different doctrinal priorities. The Soviet Mosin Nagant, dating from 1891, was a simpler and rougher design in many of its mechanical details. Its bolt generally required more force to operate, and its overall machining finish was less refined than the Mauser's. But the Mosin Nagant was rugged, tolerant of poor maintenance, and enormously cheap to produce in the quantities the Soviet Union required. It did what Soviet doctrine needed it to do. Individual soldiers may have noticed the Mauser's smoother bolt operation when they handled captured examples, but generalizing scattered anecdotes into a broad Soviet preference for the Kar98k would overstate the evidence. Now, The Mauser 9.8 action was not without its own significant drawbacks. It was expensive and time-consuming to manufacture. The controlled feed extractor required precise machining. The overall action demanded more manufacturing labor than simpler competing designs. As the war progressed and Germany's industrial situation deteriorated, late-war production suffered visibly. The Kriegsmodell variant, introduced in 1944, eliminated the bayonet lug, cleaning rod, and other features. Stocks were left rough and unfinished. Machined parts grew coarser. The fundamental bolt mechanism remained sound, but the rifle built around it showed the strain of a collapsing industrial base. The evidence tells a more nuanced story than the usual narrative of simple superiority or obsolescence. The Mauser 9.8 bolt's influence on subsequent rifle design is well documented and substantial. The pre-1964 Winchester Model 7.0, widely regarded as one of the finest commercial bolt-action rifles of the 20th century, used a controlled round feed action descended from the Mauser 9.8. The Ruger M77 drew from the same well. Numerous premium bolt-action hunting rifles manufactured throughout the 20th century incorporated Mauser-derived features, particularly the controlled feed extractor and front-locking lug geometry. That said, describing the design as permanently unmatched would be misleading. Modern precision bolt-action rifles from manufacturers like Accuracy International, Tikka, and others have introduced significant refinements in metallurgy, machining tolerance, trigger design, barrel technology, and modularity that go well beyond what the original Mauser 9.8 offered. Some modern designs deliberately use push-feed actions and achieve outstanding reliability. The Mauser 9.8 established a benchmark for its era and for a specific set of design priorities. Subsequent engineers have both built upon it and, in some applications, moved beyond it. What remains true is that for dangerous game hunting, where a feeding failure at close range from a charging animal can be fatal, controlled round feed actions descended from the Mauser 9.8 are still widely preferred by professional hunters and guides. The system's core advantage, positively controlling the cartridge from magazine to chamber to ejection, retains practical value in that specific high-stakes context more than 125 years after its patent. And soldiers discovered something that specifications alone could not fully capture. The tactile quality of cycling the Mauser bolt, the feeling of the lugs rotating into lockup, the positive feedback of the controlled feed engaging a cartridge, created a sense of mechanical confidence. This is subjective, and different shooters describe it differently, but it appears consistently in accounts from soldiers, hunters, and competitive shooters across multiple generations. There is something about the way the action feels that goes beyond what a data sheet can measure. Remember that German rifleman near Stalingrad? Temperatures well below freezing, snow in his equipment. He worked the bolt and a fresh round fed into the chamber. That was not a miracle. It was the accumulated result of decades of iterative engineering by Paul Mauser and his successors. A controlled feed system designed to function across a wide range of conditions. Front-locking lugs built to handle pressures well beyond normal service loads. Gas venting to protect the shooter when ammunition quality varied. That is the lesson of the Karabiner 9.8k's bolt. Not that it was perfect, not that nothing has equaled it, but that thoughtful, integrated mechanical design, built around specific failure modes and real-world operating conditions, can produce something whose fundamental logic endures long after the context that created it has passed. And that is why, more than 8 decades later, when rifle designers sit down to build a controlled feed bolt action, the Mauser 9.8 remains one of the first designs they study.